stick with me here. Okay. So we are investigating the heights of 16-year-old American males. Say we know that the population average height, I'm just going to read mean as average because I think it sits well better with us. The population average height we know is 65.3. And a standard deviation of 4.2. So, not that this is necessarily what we did the other day, but just to pause for a minute, because I know the concept of standard deviation is fairly new to us. Okay, the average height for a 16-year-old boy is 65.3. And with a standard deviation of 4.2, one standard deviation away would be 69.5. A second standard deviation away would be 73.7. You trust me? I don't trust myself. Subtract 4.2, 61.1. Subtract another 4.2. Oh, now I really don't trust myself. 56.9. Okay. So they're giving us the population average and the population standard deviation. How they know that, I don't know, but they're pretending. Say we know that. Okay. Then let's say we take a sample of these teenage boys. The sample has a size of 30. So we're going to randomly grab 30 16-year-olds. Will their mean height in that sample always be 65.3? Yes or no? No, of course not, because there's the luck of the draw. No. And it's really because of sampling variability. If we took samples 100 times, none of them may be 65.3. In fact, sometimes if we pick from the wrong, if we pick it the right way or the wrong way, however you want to look at it, I might see an average height of 70 inches in one of my samples of 30 kids. I might see an average height that's way lower at 60 inches if I get unlucky and I pick a bunch of short kids. But the reality is, if I did take a sample 100 times over, they would probably average, the average of all of those averages would probably be around 65.3. So sometime, like one sample I might get as low as 60, another sample I might get as high as 70 as my average height within that sample. But on the average of all of those averages, it probably would come out close to 65.3. So could it be significantly different? Yes. Do you think it would be significantly different 80 times out of my 100 times of taking a sample? That would be no. But once or twice, might it be as low as 60 inches? Yes. So on our computer, there's another program called NormSamp, which I'll pull up. It's right there next to the simulator for proportions that we did yesterday. And it wants us to run the program with the mean and the standard deviation, like the population we're looking at right now. And it wants us to actually go ahead and take samples 30 times over. This one is saying to do at least 200 simulations. 500 is preferable. Fine. State the minimum and maximum of the sample means. The mean of the sample means and the standard deviation of the sample means. So, I'm going to go to my website. I have to go, I want the sample proportions. I want the sample norms distribution. Sample norms, NormSamp. Yep, this is it. Okay. So the population mean, population average height is 65.3. The population standard deviation is 4.2. The number of simulations they said to run at least 200. We'll do 200. The sample size is 30, decimal accuracy 2. So I'm going to run the simulation, hit OK. Okay. This list here, sample means, I ran 200 simulations. There are 200 different averages here. There's 200 items in that list without counting them. The lowest I ever got was 63.32. So I grabbed 30 kids on one of these 200 occasions, and I took those 30 kids, I averaged all their heights, and it was 63.32, which is lower than the population average, but not by as much as I thought. Not that I knew, I just threw out 60 as being the low end. So on the lowest end, 63.32. So write that under your minimum sample mean, 63.32. That was the worst case scenario when I picked the shortest kids by chance. Maximum sample mean was 67.16. And again, you're all going to be running your own simulations on your homework, and our numbers will all be different, but they should be in the ballpark. Everyone's low will probably be in the ballpark of 63, and everyone's high will be in the ballpark of 67.16. Okay? So do you see how that 63 to 67 surrounds the 65.3 pretty nicely? Sometimes we get very lucky and we get a 67 average on the high end with the 30 kids we pick, and sometimes we get a 63 on the low end of the 30 kids we pick. This number, though, is the average of all of those 200 averages. So each of these 200 experiments have their own individual average. When I average those averages, I get 65.19, which should be pretty darn close to the population average, which was 65.3 up here. Everybody see that? So fill that in on your notes. The mean of the means was 65.19. Now, by the way, if I had done 500 simulations, in theory, that should get even closer to the population. So what this simulation is actually doing is it's actually going out and taking random samples of 30 kids from this population without actually having to physically go and do it. And the standard deviation of the means should be very low, with not much variation. So put that in with 0.8. Of all the stuff that we just looked at there, the standard deviation of the means is probably the thing we'll look at the least often. Okay? So down below, how does the variability of the sample means, that's here, how does that variability of that list of 200 means compare to the variability of the overall population? It's much less, right? Much less. So just write that. It is much less. Because by averaging it, you're already centralizing the data. So the variation of averages is going to be less than the variation person to person. And then in E, state the mean of the sample standard deviations. Let's skip that. We don't need to do that. Skip it. We should get rid of that for next year. And then we'll be done with that example. That's essentially the average of the averages experiment. Down below here, I just wrote a quick thing on notation. If you see X bar with a little bar over it, that's the average of the sample you took. Versus this U with a bar over it, that's the average of the entire population. So up here in this problem, the U with a bar over it would be 65.3. And then each of these samples averages would be an example of an X bar. So one of our sample averages was as low as 63.32. And, you know, that's the lowest, x sub 1, and I'll make this x sub 200, because that was our 200th samples average. And we had 200 of those mini sample averages. So that's just a quick thing on notation. And then we're going to switch gears, although it looks like we're still talking about 16-year-old boys and their height. So Mr. Weiler took a sample of 30 16-year-old males. So someone actually went out and did this, okay? Someone took everything else has been simulated. Someone's actually going to go do this now. They're going to grab 30 16-year-old males, and they're going to calculate the average height, and he found it to be 66.4. So X bar is 66.4. So just quickly to wrap your head around this, does it look like his group happened to be a little bit taller or a little bit shorter than the population? Right. Slightly taller than U bar. It's just worth wrapping your head around. But is that slightly? A full inch? A full 1.1 inch? Maybe he was choosing from the basketball team, because then there would be a bias. Or maybe it is coincidental. This is what the simulation is going to tell us. Where does 66.4 fall on our distribution? So if I go back to that same one that I had already run, I don't need to rerun anything, and I go down here, where does 66.4 fall? So if you, by the way, hover over these, you see the exact number, 66.29, 66.25, 66.4748. Okay? So I'm going to count, and by the way, there were 200 simulations, so there's 200 mini rectangles here. Of the 200 mini rectangles, how many were 66.4 or even more extremely tall? Do you follow? Okay, so we're going to kind of quantify what is the likelihood this was due to chance and coincidence, or what is the likelihood there was a reason behind why his sample was taller. Maybe he chose from the basketball team. So you can do it on here, or because we have a list, we can just go and count. 66.4, oh, that's a lot. 66.4 or taller. Okay, so I'm going to start counting here. 1, 2, 3, 4, 5, 6, 7, 14 out of 200. 14 out of these 200 simulations. So I'm going to write that. 14 out of 200 in our simulation were as tall as 66.4 inches or even taller. That means, what percentage is that? 14 out of 200 is what out of 100? 7%. That means there's a 7% likelihood that his sample was taller due to pure coincidence. The simulation will give you the percentage that it's due to coincidence. It's not low, it's low, but it's not overly low. You don't, again, it's hard to come up with like a concrete answer like yes or no and actually be firm about it, but you lean in a certain direction. If there's a 7% likelihood that his sample was taller due to pure coincidence, on the flip side, that means there's a 93% likelihood that his sample was taller due to a logical reason. And that logical reason is what they may ask you to hypothesize on. Maybe he pulled his sample from the basketball team. Maybe he pulled his sample from, I don't know, what else would cause people to be taller than normal? I don't know. Maybe they lived near a field where steroids were buried. I don't know. I'm making stuff up. Who knows? Maybe he pulled from a town where for some reason a lot of families have extra, what's that, human growth hormone in their systems or something. I don't know. Who knows why? But there's a 7% likelihood that his sample was just purely coincidental. Like he just, luck of the draw, picked taller people. But there's a 93% likelihood that his sample was taller due to a logical reason which we could hypothesize about. And so, and this is where we can vary. Do I believe that his sample came from the population? I don't. I think that 7% is low enough to say, you know what, something else was going on here. It wasn't just that lucky or unlucky. So do I believe my answer, and again, we all could differ here, I would say no. My gut is that no, it didn't come from the general population. He was camped out someplace where there were more tall kids. And my reason would be no, because a 7% chance of coincidence seems too low. That would be my why. Or why not. Examine the results of my simulation. I already did that. Okay, so maybe I prematurely did my simulation. And they say to quantify how likely. I already did that. That's my 7%. How likely was it that this sample came from the population? Only 7% likely. Okay? The reality is there's a much bigger chance that it came from a scenario where he was camped out grabbing kids that had a more of a chance of being taller. So it wasn't really a fair grab of kids. He was standing outside basketball practice, outside the gym, and maybe those are the 30 kids he grabbed. Okie doke? All right, so again, don't worry about the back. The simulator is up there. Your homework is coming.